for different problems, scientists come, again, going back to that spectrum, right? Scientists think about things in terms of their models, right? And so this is a purely science-driven approach, where statisticians think about things in terms of just data, purely data-driven approach with little science. And I would like to see a conversation, right? Perhaps not a debate, but a conversation, discussion about, where is that optimal point in the in between science-based and data-based learning, right? Which will give you the most bang for your buck, right? Give you the most efficiency for and the maximum power for the data that you observe, which in many cases is very expensive. And this conversation, I think, really is domain specific. And it relates, it can sort of spur a lot of interesting developments in both the statistical modeling literature as well as, how we perform the sort of scientific discovery pipeline, right? Because it involves thinking about, well, what information should I integrate, right? And maybe it's not all of the information, because if I integrate all of the information, I'm basically back at the beginning with the scientific model being too expensive, right? But think about what information we can integrate, what information is important, right? And how do we sort of integrate that model in and give you scientific conclusions which are interpretable, right? Are efficient and, are useful, right? So, I think that's one area where it really deserves further discussions between scientists and statisticians. And I think, I think both sides have to be sort of open-minded and sort of thinking about how we integrate aspects from the other side in terms of building, workflows that are, that can be used in light of these, very expensive, very sophisticated, but very expensive experimental procedures.
Hi everyone, today's guest is Simon Mack from Duke University. Simon's research is in integrating scientific knowledge into AI and machine learning models. And I think what he really epitomizes is this sort of a creative, scientific, critical thinking. Furthermore, Simon does some of the best statistical presentations that I have seen. If the Occupy movement were directed at statistical presentations, they'd be coming after him because he's definitely in the upper 1%. So Simon, welcome to the show. I'm really looking forward to this conversation today.
Yeah, thanks for having me. This is really exciting.
Yeah. So just on the topic of integrating domain knowledge into AI and machine learning algorithms, anyone who's listened to a single presentation has known that experts always emphasize this thing with important of using domain knowledge to get started. And this usually comes in the form of data collection or data wrangling or, how to interpret a model, things like that. But your work definitely seems like crank it up to 11, where basically you're directly embedding or interfacing with the physical or mechanistic principles of we'll just call it the stuff that you're working on because it's quite varied. So how would you say that, how is your work different from just saying, I keep the domain knowledge in mind when modeling? What differentiates your approach?
That's a great question. I think one of the things that really differentiates, this idea of just integrated domain knowledge is that, in a lot of the problems that I work on, there's really this need for integrating more information in order to allow the problem to be solved. So one example is this problem that I've worked on, on building new, next generation rocket engines for spaceflight, right? And this, this idea of building new rockets is, very expensive process, right? So if we're going to think about changing different parameters, then, we have to think about, well, do I want to prototype a new rocket and then, test it out using physical experiments? Or do I want to build it on the computer and then test it out using virtual experiments? And in both of these cases, the testing procedure is very, very long, right? So very expensive, very long. And oftentimes we can only get, it can take millions of CPU hours, billions of dollars in prototyping costs, right? So we can only have maybe 5 or 10 data points. The data that we get from these, engineering problems is very, very little. And that's really, from a statistical perspective, right? This is one of the things that we were challenged with in the project is if you have 5 data points or 10 data points and you want to do perform prediction over a high dimensional space, there's nothing in statistics that would allow you to do that in a feasible way, right? If you only have 5 or 10 data points. And that's really where the science really comes back in, right? It's necessary in terms of improving your predictive models. And oftentimes I like to think about this from like a Bayesian perspective, right? So the idea is that, well, I have actually more information than I think I do, right? The scientists which generate the data, the underlying mechanistic models, underlying physics for the problem, can sort of serve as prior knowledge, which we can integrate into a Bayesian model. And that can add in additional information, right? Which can supplement the 5 or 10 data points that I observed, right? So this idea is really necessitated, right? This integration of scientific information as priors is necessitated by a lot of these very, very expensive sort of experimental problems. And without the science, the problem is, quite frankly, infeasible from a computational or a budget perspective. Yeah.
Yeah, I definitely like to come back to this issue of the computational infeasibility and where it becomes a black box. But just to begin with, you mentioned physics, and physics is obviously the most obvious domain where you can just have these strong enough domain knowledge to incorporate into the modeling. But is there a boundary cutoff where you can basically say like, my domain knowledge is sufficiently strong versus I don't know enough?
That's a
I'll
great
just
question.
basically say like, well, because the example, it's like, well, I'll just make sure that my model doesn't conflict with reality or common sense. And I view that your work is on like a different plane than that.
Yeah. No, that's a great question. So I work more in the area of engineering statistics and statistical modeling with physics applications, right? And it's indeed in these applications where in a lot of cases, the scientist knows, at least the models that they use, a lot of the basic principles they know with quite amount of certainty, right? For example, if I drop a ball, right, and it goes down to the drops down to the ground, I know a lot of the physics that goes on there, right? And this is in contrast to a lot of work in the biological sciences where there could be many competing theories, and because of that, right, it's much more difficult to integrate in the sense that I'm working on integrating some of the scientific knowledge into the analysis. So as an extreme point, one of the areas that I work on is called computer experiment emulation, right? And this is where we're actually so you can sort of think about it. Let me sort of extend that rocket engine example there, right? I can build a rocket engine directly in the computer, right? I can program it in, and then I can solve the underlying PDE equations, right? To at least simulate what might happen within the rocket, right, during spaceflight. Now, the scientist has to code this in themselves, right? There's a certain set of PDE, certain set of mechanistic equations that they have to code in, right? But in order to solve one of these systems, right, it can easily take millions of CPU hours. But the data generation procedure, like the actual science there, is known with certainty because the scientists use those principles to generate the data, right? And in those cases, right, integrating that type of prior information, would definitely help, would definitely benefit, right, the predictive model. Whereas in cases where you observe, the data in reality and you have to postulate some sort of theory or some sort of a scientific prior knowledge there, that might be, you might have to, investigate that a little bit more carefully about, whether or not I can actually trust this model, whether or not the principles actually hold, and that's going to be a more complex topic.
Yeah. Sort of. It also seems to me where essentially you have these very like mechanistic models, the types that you're describing with the rocket engine work that you did, which by the way creates some like very beautiful images, and then maybe just like on the other extreme of the spectrum, we have these like highly phenomenological models where effectively it's just like features correlation, pop it out, and but you've also worked on things, for example, with like your aortic, aortic modeling, where effectively your scientific baseline is actually empirically derived. So effectively you have this essentially this empirically derived function, but you also have some physics behind it as well. And so I know this is super murky, but like, is there any type of cutoff or any sort of like decision zone where you'd be like, okay, this is too phenomenon based versus mechanistically based?
Yeah, that's a great question. And that really, in all, in any form of the sort of science integrated modeling, there really has to be a conversation with the scientists, right? A close discussion about, look, what type of prior information can we leverage into the problem, right? And how certain are you about that, prior knowledge, right? And I think that's where a Bayesian perspective of the problem again really comes into play, because we can set the strengths of our priors, right, based on the scientist's prior knowledge. Now, again, going to the extreme of the case where we have these virtual experiments, right, where the underlying sort of physics are already coded in, and that's part of the data generating model, right? In that case, I can use those principles as long as they can integrate within the predictive model nicely, right, with certainty. I would imagine in other cases, definitely in the biological setting, which I don't work too much in, it's a much more challenging area for some of this work because, like you said, there are many competing models, and the science is still to be discovered in a lot of these cases, right? In these cases, one would have to do a careful sort of inspection, discussion with the scientists, maybe hypothesis testing of some of the science first before you integrate that into your predictive model. Right? And I think that opens up, perhaps a really interesting area as well, which is, look, if I were to do hypothesis testing of certain scientific models, right, with the goal of integrating some of that information within prediction, then how would I do so in a statistical fashion, right? And that really goes back to what type of scientific information are we integrating in, right? So I've done a little bit of work on hypothesis testing, for sort of shape constraints, which one can view as sort of scientific information, right? For example, if I drop a ball, right, and it falls down to the floor, right, there's some sort of monotonicity going on there, right? The ball's not going to magically jump back up in the middle of the air. And that quote unquote science, even though it's quite sort of intuitive, right, it can be viewed as a shape constraint, right? And therefore, if we wanted to test whether or not this phenomenon holds in practice, right, sort of translates back to the problem of testing whether or not certain shape constraints hold, right, statistically. So there's an interesting line of work there, definitely, but that has to be sort of done before we integrate that information within predictive modeling. Yeah.
Hey folks, we're a few minutes into the show. This is usually the part where the podcaster talks about their sponsor or something. I'm not going to do that, but I will ask two things. One, if you could leave a like or a dislike based on your preference, and also let me know what you think about this topic, and also what topics you like discussed on future episodes of the show. That's it. Enjoy the episode. That's cool. That would actually be maybe for a future conversation as that type of work develops, because it'd be cool to hear some of the more challenging examples of that, where effectively you are trying to first hypothesize and learn essentially the essential science that's required, and then you go the next step of actually including it in the model. So
Now, maybe sort of one more point on this. I think that's okay. And I think the idea of sort of testing for constraints, right? Testing for whether or not scientific principles hold. I mean, this might not be scientific principles, but this might be sort of economic principles, in the area of finance, right? Certain pricing principles that we follow. And this is actually quite interesting in the area of finance, because if we're thinking about testing for constraints there, then, the violation of these constraints actually mean profit opportunities, right? So, this type of idea really sort of extends to a lot of different areas beyond, maybe the standard sort of scientific applications, right?
Yeah, that actually just off the top of my head, it reminds me of one of those ways that you could use like a linear program to identify arbitrage scenarios, where effectively, you just pop it, and if it never converges, then effectively it's something like that where you found an arbitrage scenario.
Yeah.
Cool. Just sort of to loop back on this one thing, like when we talk about scientific knowledge that we have and we don't have, there's a point at which we will call certain things black boxes. And I guess sometimes that's a knowledge component. And then I guess other times, it could actually just be a computing burden, where effectively it's black box simply because we lack the computational ability to run such a sophisticated thing. So effectively you could run the direct simulation, but it takes so long, it has to be black box. What are sort of the considerations there? Is it just essentially is like a bottleneck, where whichever one you achieve first, it becomes a black box from there?
Mm-hmm. No, that's a great question again. And I think this actually relates a lot to some of the work that's actually been done on black box optimization, right? The idea of black box optimization is, look, I have a certain objective function, which we consider to be black box because, like you said, either we don't know a lot about it, or it's just very computationally expensive, right? And we try to optimize this objective function under these constraints. Now, there's actually been an interesting line of work recently on what's called gray box optimization, in which one tries, right, to open the black box up a little bit, but not the whole way, right? And this is really, very much similar to this idea of integrating some sort of domain knowledge on the black box, such that we can model the function, right? And oftentimes, that's where a lot of my research comes into play, because in a lot of cases, when we're trying to integrate some of this information to make this gray box, we would need probabilistic models which are flexible enough to integrate, right, this type of information. That's where a lot of these Gaussian processes come into play, right? They're very flexible probabilistic models in which you can integrate a wide variety of prior information into there. Now, I would say, especially in the area, the research that I do, where the data is actually very expensive to collect, right? Whether or not that be physical experiments or virtual experiments. Oftentimes, I mean, there's two reasons behind this, right? The first reason that we want to integrate some of this information, and instead of considering everything as black box, is we need to, right? The project, there's maybe like 1 million CPU hours for the project, but the program officer wants to see, the model work well, and you get scientific conclusions up to a certain precision, right? And if you have 5 to 10 data points, it's very difficult to do with just statistical methods. And that's where we really have to sort of talk with the scientists very carefully and integrate a lot of this information in, such that we can get the objectives that we want. I think a different perspective on this, different reason why we want to do this, is we want to make the models interpretable as well. Right? So this again, this goes back to the topic of interpretable machine learning, interpretable statistical learning, right? Because oftentimes, especially when we have limited data, the resulting model. So, for example, if I use the example of a ball dropping down to the floor, and I sample at each time, where that ball is at, right? If I sample this very sparsely, then if I fit some of these very powerful machine learning models, right? Deep learning model, whatever, it can very well say that the ball could drop down, and then at a certain point in time where it's sparsely sampled, go back up a little bit, right, and go back down. It's just minimizing the prediction error, right? But then a scientist would take a look at that, and we had a lot of experiences with this in some of our projects, right? We learn from our mistakes, right? The scientist takes a look at that model and they say, look, I'm not going to use this because the ball's never going to go back up.
You just be like, oh, no, it's fine. It's just a little wiggle in gravity. It's like
That's right.
gravity was there, it wasn't, it comes back.
So as a statistician,
It's
you
like
say,
a house cat.
the objective function we're minimizing is the prediction error, right? And so in this case, even though it gives you this really, and I'm using a very obvious example, right? But physically, some of these properties, the scientists would look for before they use the model, of course, right? It's not just a data crunching game. So in a lot of these cases, we want to make the model definitely interpretable. And match what the scientist a priori believes, if they have a strong belief on this, right? And this is another reason why we oftentimes, at least for our projects, right, want to sort of open up that black box, right, such that the models that we get out, that the scientists will be using for scientific inference, is something that would make sense to them.
Yeah, cool. Before we go on, I was just wondering, like, outside the physics example that you just gave, are there examples of integrating scientific theory into other machine learning models? So you mentioned like the econometrics type stuff, but I was wondering within the realm of science, are there any sort of really good examples of
Let me think a little bit. So I worked on a couple of projects. I talked a little bit about this rocket engine design project where the physicists have, a lot of these fluid mechanic principles that they want to apply there. Um, I'm currently working on a project where um, this is a performing, predictive modeling of heavy ion collisions. And the idea why we want to study heavy ion collisions is they really form the basis of the formation of matter, right? Shortly after the Big Bang. So it's an important topic there. But these simulations are very expensive. Now, in order to study some of this, right, a lot of times we have to integrate models of different accuracies, of different scales. And that's, I think, a really key topic that's arising in sort of this application, this sort of interface between science and statistics, right? Is that given the computational costs and given sort of the advances in experimental technology and computing power, we're able to perform very, very sophisticated experiments, but at great costs, right? And oftentimes, especially when we do a predictive model, we need more data, right? And so one way of getting more data is perhaps integrating the science. But another way of getting more data is why not just run the scientific models or run the experiments at lower accuracies, right? But these experiments would be a lot faster, a lot cheaper. And then comes the statistical question of, look, I have experiments with high accuracy, experiments with low accuracy, maybe different types of lower accuracy. How do I integrate all of this together? Okay. And that's actually another area where, this integration of science into statistical modeling really comes into play, right? Because in a lot of these cases, we're able to draw the connections between, how a lower accuracy experiment is related to a higher accuracy experiment. We can model this thing probabilistically and model the correlations, right? And integrating this scientific information to build what we call this multi-accuracy or multi-fidelity prediction model really relies on the scientific information about model dependencies. So that's another area where the science really comes into play, and it's making an impact in a variety of different fields, definitely in physics, right? In terms of that nuclear physics example, the heavy ion collisions, but also in terms of other forms of physics and engineering sciences. Yeah.
Yeah, actually on that, because one of the themes that I noticed in your work is that a large number of your applications essentially had to deal with handling science at different scales, essentially phenomena at different scales, where you would essentially have like these high, like long length scale components of your process where presumably there's very little variation, and effectively with little variation, it means that you don't need to run too many computations. And then there's the short length scale. So you can think about like the short length scale Gaussian process where you can have this high amount of variability within a short period of time. And effectively that means that you have to sample many, if there's a high derivative, you need to essentially sample frequently to figure out where things are.
That's right.
And so it seemed like that's a common theme, and also to me, it seemed like the that autocorrelational work that you did with the like different fidelities, where essentially you have the sort of like a set of experiments where it's just like basic assumptions and then a subset of the outcomes on those, and then effectively you added more rigorous physical principles. Like in a medium fidelity model, you would have like these idealized liquid mechanics, and then in our fluid mechanics, and then in the highly computational one, you'd have like the viscosity, like the viscous fluid mechanics and type of that stuff where effectively you move between these different fidelities. But to me, it seemed like a lot of those were essentially challenges with handling the data at different scales. Is there, to me, it seems like that has to be inextricable from the nature of science, where effectively we are, one of our big challenges between these different fields is we're effectively just trying to handle things at different scales. And it seemed like effectively, it's funny that someone working to embed scientific principles into this modeling effectively is trying to piece together, stitch together these different scales. It's as if you're essentially trying to combine the different disciplines, but you're doing it in a statistical or
statistical fashion.
fashion. Yeah.
That's
So
really where the challenge is in terms of building these models, right? So, some of the work that we do, right, is dealing with predictive models, right? These multi-fidelity models, but in many different ways that we can imagine this from the sciences. So, like you said, multi-scale is one aspect where we think about different scales of the experiments, right? And we have flexibility in changing these scales in the experiment. Another aspect is multi-stage experiments, right? So you can sort of imagine the case where we have this, heavy ion collisions problem that we're working on, where we have two heavy ions, right, colliding with each other, right, and near light speeds. Now, this simulation is clearly going to be in parts. Like if we're going to code this up on the computer, right? We start off with these things, shooting at each other with very, very high speeds, colliding, right? And the nuclear theory says, when they collide, we can sort of model the plasma that's created using fluid dynamics, right? And once this collides, and then this plasma, what we call the quark gluon plasma, forms, in this, very, very small time scales, right? It rapidly cools down into matter. So that's really, the plasma is what's theorized to be present, shortly after the Big Bang. This rapidly cooled into matter, right? But you can imagine this type of simulation procedure is definitely in multiple stages, right? We have to set up the collision, we have to let the collision happen, and then we have to let it cool down. And at many of these different stages, we would use different physics models, right? Multiple stages, right? And these different physics models, all of them can be run at different stages, right? And so the challenge is really to integrate, trying to sort of put the scientist's modeling mind, right, from the physics into the statistical model, and think about how to sort of model linkages in that fashion, right? So there's a lot of different ways that we can have these sort of multi-fidelity experiments, but integrating them, within in a way that respects the science within a probabilistic model is one of the really interesting areas that is really finding a lot of cool applications in the physical and engineering sciences. Yeah.
So for example, in one of the ways that you did it for effectively, you're looking at like the autocorrelation between these things. And in the example, I wasn't sure how much detail would be worth going into, but effectively, like, to me, that made sense given the nature of it, because effectively there's this sort of like, there's a process to it. Essentially, there's essentially, it did seem autocorrelational, but are there other types of sort of correlation or linking that are possible other than what people might just broadly imagine is like, oh, we're just looking at the correlation between these things, like saying scale A is correlated with scale B like this?
That's a really good question. Yeah. So correlations are one way of modeling for model linkages, and we have a recent paper coming out which thinks about correlations in terms of a graph. So you can imagine, I have a node where this is a very high, like the highest accuracy experiment that we can have, but we can have multiple ways of going down from this.
Mm-hmm.
We have data that spans multiple, multiple scales and multiple stages, right? That can be simplified. And so, we can represent this thing in terms of a graphical structure, again, with the correlations between each of the edges. Another way of thinking about linkages, actually, is in terms of the scientific models. Oftentimes, I think most of the time, right, these linkages are much more than correlations.
Mm-hmm.
So one example would be in the case where, let me think a little bit about this. Let's say there's some sort of approximation, right, which goes on in terms of the simulation. Now, we can do a direct simulation of a certain phenomenon, right, and that requires solving the PDE. But there might be a quicker way, which uses some sort of spatial averaged approach, right? Some sort of sliding window over space or sliding window over time, which sort of discretizes, right, the solver. And we would get results much quicker, much more computationally efficient, but at the cost, right, of losing spatial resolution or temporal resolution. But in cases like that, right, there's a certain linkage between the high fidelity or the highest accuracy model and these sort of spatial averages, which is really a limiting relationship if you think about it, right? Because as we make the resolution finer and finer, we would approach the true solution, right? And so incorporating this within a probabilistic model, incorporating this sort of limiting behavior, is also one really interesting direction, right? And this is really much more than saying, look, I have the lower accuracy experiment, higher accuracy experiment, and they're correlated by some correlation rho, right? It's really describing this sequence of limiting behaviors that we have to model probabilistically, right? And there's a lot of different cases that we can think about, right? Different types of model linkages from a scientific perspective, which really necessitate different modeling techniques from a statistical predictive model, right? And integrating this type of prior information on what the scientific linkages are, should give you better predictive performance, right? If the assumptions are correct.
Cool. Just to sort of, I guess, circle back on that. So, for example, like on this linkage issue. So, for example, like low pass filtering on sort of like highly noisy data. Is that an example of this sort of? Is that sort of like an example of like how you'd be linking it, but it would be there's a limitation to it. But as you essentially remove the filtering, essentially you're approaching the limit of what the true underlying.
Right. So in some sense, and this is one of the, some of the works that are, recently in the literature, which is, look, in a lot of cases, right, if we assume we have a Gaussian process, then we're assuming that a priori, right, at different points in the parameter space, we have, if you use a stationary kernel, then we have, constant variance. A priori, we assume that the surface has constant prior uncertainty over the whole region, right? But if you think about some of these experiments where we might have a certain parameter, call these things typically fidelity parameters, right? Where, as we get closer and closer to zero, we get closer and closer to the true solution, right? Let's say from the approximation, but, it becomes more and more expensive to solve, right? But if you think about, in terms of just modeling our prior variance, our prior variance about, what the response surface looks like, as we decrease this fidelity parameter, right, we would a priori have more and more certainty, right? So if this parameter were very large, so this was a very coarse resolution experiment, then we would have high variance, but we would progressively have lower prior variance, right, as we increase the fidelity. And, just something as simple as this, right? We could use something, just from our prior assumptions, a standard Gaussian process might not be the best choice. And we might want to use something like a Brownian motion or something like that to sort of model the sort of decreasing variance behavior, right? And so that's one approach that we can use to integrate this type of prior information. Yeah, but it really depends on what type of linkages these are, right? This could be this limiting behavior. This could be an averaging type of behavior. This can be many different things from the scientific model. And each one of these different linkages really sort of open up an interesting sort of a new statistical approach which can model this, right?
Would you mind? You mentioned essentially like the graphical model representation. Would you mind sort of talking us through that? Because that seems really interesting to me. Because effectively, you're making a very hard description of the interrelationship between these different.
That's a great point. So the idea in terms of this sort of this is a very recent paper that's out on Archive.
Mm-hmm. And I'll pop up the picture of it. So yeah, if you just want to, yeah.
The idea here is that, well, we might have one very high accuracy experiment that we want to predict, right? But we might have many sort of lower accuracy representations of this experiment, right? But they're linked scientifically in very different ways. So again, maybe think about the case where we have that heavy ion collision experiment, right? Many different stages, right? And so we start off with the high fidelity or high accuracy. I use the word fidelity for accuracy. We start off with the high accuracy experiment, but at each of these stages, I might want to run something that's a little bit cheaper, right? So let's say if there's 3 stages, and for each of those, I decrease the fidelity a little bit. Then I sort of get 3 different ways of decreasing computation. right? So if I try to represent this thing as a graph, right, we would start off with the first node, right, top node, the root node, as the high accuracy experiment. But I have three ways of going down, right, into lower fidelity representations. And in a lot of these scientific problems, at least in the ones that I work with, we can really sort of talk with the scientists a little bit and think about, well, what type of lower accuracy experiments can I use, and how are these linked together, right? How are these sort of model dependencies linked together from a scientific perspective? But if we think about combining all of these dependencies together, from a mathematical perspective, we will have we can think about this as having a graph, right? A directed graph, which is connecting all of these nodes representing different experiments. And so that's really one form of the science as well, right? This particular, what we call a fidelity graph, right? Which links together the data that we have on hand or the data that we will simulate. And so, integrating this graphical structure within a predictive model, this is one of the recent papers that we have. We found that, by integrating this graphical structure in within what we use, the tool that we like to use is a Gaussian process, right? But if we integrate the structure within a Gaussian process, we will get, oftentimes better predictive performance than ignoring the science altogether, right? This is really important in a lot of these problems where, again, the data's on the high accuracy experiment, the data is very, very limited, and any sort of savings will save the engineers, 2 or 3 times the cost, right? They'll be very happy to hear that. Yeah.
Cool. Yeah. So I guess one of the things I think is interesting is like, I get the idea of how, the highest fidelity experiment is sort of this like the top node, and then effectively you'll have lower fidelity parameterizations, I guess, if you will, that stem from that. And then I guess by virtue of them all being connected, all the parameterizations of the low fidelity experiments being connected via that top high fidelity mode, I guess one of the things I was sort of turning over in my head, you might have seen me thinking about that, is like, what does that mean about the conditional independence of these different fidelity sort of parameterizations?
Yeah, that's a great question.
Conditional, because I definitely like that description, that effectively what it's saying is like it's all stemming from the reality that's at the top. And if you effectively condition that out, you don't need to know what's in the other ones. But would that be the case? Sorry, and anyway, so that's what I was thinking about. But I'll let you talk. Sorry.
Yeah, no worries. Well, it's great that, because it's worth thinking a little bit. So, in terms of formulating our model for that paper, right, which we call the graphical multi-fidelity Gaussian process, right?
Which is a really cool paper, by the way.
Creative name. Yeah. We could have thought about a better name, but yeah. So the idea there, by forming the Gaussian process in such a way, we will get some sort of conditional dependence statements out. This essentially what we do is we build a conditional Markov model, I think, and we sort of we can show that this particular model has certain properties which imply certain independence assumptions on the simulations. Right. So the idea is that, well, if I observe, right, if I have a high fidelity experiment and I observe its immediate lower fidelity components, then anything outside of that really tells you no additional information about the high fidelity experiment, right? And we can sort of show this thing statistically about the models that we will integrate. Of course, we should run these, assumptions past the scientists and say, this sort of makes sense. What we're assuming about the sort of independence, this type of information, right? Assumption about the model. And I think this type of direction is actually quite similar in some sense to the assumptions that are made in Bayesian networks as well, right? Where you have an underlying graph, right, and you leverage some sort of conditional independence assumptions there to build up, a probabilistic model where you can sort of filter information throughout the graph, right? Yeah.
Yeah, that is really helpful. Because I couldn't help but think about I like that a lot, and I was trying to think through it, and it's like, oh, well, why don't I ask the expert while he's right here, for some of that intuition. So I guess one of the other things is, maybe for the people listening, they might have heard, a lot of things. You have these like GPs, you have these essentially network GPs. We have our, physical equations and everything like that. And we had the large eddy models and things like that as well. So there's a lot of pieces, a lot of tools floating around, and I was just wondering how much model innovation is required for the work that you're doing versus how much of it is you effectively just like innovating, by which I mean like actually grabbing the different pieces and putting them together in the most sensible way. Because it seems like you've done a good bit of sleuth work.
Yeah, no, that's a great question. Indeed, when we sort of deal with applications and when we talk with the scientists, the problem is much more complex than what existing methods can deal with, right? This notion of like integrating science, right, within these predictive models is at least in terms of the GP case, is still a relatively new area, right? But of course, when we talk with scientists, they have a lot of different scientific information that they can integrate in. Each of which, right, if we just break apart this problem, each of which can be a really interesting paper in and of itself, right? So a lot of the work that I do is really trying to interface between the problem itself and using this to motivate, right, different statistical models which can deal with each individual component, right? And then, working with the scientists to build a model which, integrates these novel components together, right? To build something that really sort of works for them, right? Because scientific information is clearly different for different applications, right? For different physics problems, right? And to do like a convincing implementation of these for the scientists, right? To actually address the full scale scientific problems, we really need to combine, many of these tools together, right? So it's really, it's really twofold, right? The first, part of my job is to try and pull out these principles from the scientists and then develop models which deal with each individual type of science, and then combine them together in a computationally efficient and scalable way, right? To really address that problem for the scientists, right? So in the case where we do, have 10 data points, right? By integrating all of this information in a structured, scientifically principled way, we're actually able to solve that prediction problem, which is quite challenging.
Hey everyone, we're in the final stretch of our episode. And before you go, I'd really appreciate if you could give me feedback on 3 things. First, what was your favorite question of the episode? What did I do right? Secondly, what question did you wish that I asked but didn't? And third, what questions were brought up by this conversation that you'd like answered in the future? That's it. Enjoy the rest of the episode. Yeah, one of the projects I thought really epitomized this sort of multi-step, essentially this pipeline, this like scientific inference pipeline that you did was the aortic stenosis experiments. Because effectively, like when I was looking through that, it's like there's always the next step and the next step, and
Yeah.
so it's effectively was really interesting was because effectively you described the problem well, and then you start going into the details of like each step in the pipeline, and each step in that pipeline was honestly like a paper's worth in its own right.
Yes.
And it's like in that you did it well, which I thought was impressive. And then essentially we come back up to the surface and it's like, oh wait, then there's the next bit that
Yeah.
we have to do. And so I thought that was really interesting, but maybe that would just be just as a quick example, we can just sort of like describe that problem and the different steps because it also it's created such a like a semi-intuitive response, whereas like it was intuitive enough. For example, and what I'll talk about is like the the structure that you discovered. It was something where it's like it makes sense that, like, but it wasn't like sense to like mathematically perfect thing. Anyway, so why don't you describe that problem? Because I think
Yeah,
that
yeah.
people appreciate it.
Right. So this was a problem. This is a aortic stenosis project that was in collaboration with Georgia Tech Manufacturing, right? And the goal is to develop these 3D printed aortic valves, which surgeons, right, doctors can then use, right, to replace aortic valves, faulty aortic valves within patients, to sort of it's a surgical procedure to for aortic stenosis, right? But the challenge here, right? There's, of course, when it comes to healthcare and, making sure that the surgical procedure works well for the patient, right? There's a lot of things that we have to consider. And one of the key things for these sort of artificial heart valves is that we want to make sure that it fits the patient well. Make sure that it's personalized, right? Because if it's not, then we run the clear danger of this valve, malfunctioning or even worse, being ejected into the heart, right? Which is not a good thing. So the idea is that, well, in terms of designing 3D printing procedure, there are many parameters that we can change, right? That will give you different material properties, which hopefully match that of the patient. Now, but if you think about these things as parameters, right? And we want to match a certain material profile, right, for the valve. You can imagine this sort of goes back to this sort of expensive prediction problem where the amount of data is again limited because, again, if we're going to prototype these valves and actually perform experiments to get the material properties, it's expensive, right? And similarly, if we're going to, program this into a computer, right, and perform simulations on this, if this is sufficiently sort of high accuracy, then that can also be expensive. So again, we're met with this issue of limited data, but from a statistical perspective, it's actually quite interesting. This is one of the things that we explored in this paper, which is, look, the material properties, right? What we actually get to control in terms of these aortic valves is this thing, this functional form called a metamaterial structure, right? Where, we have this sort of soft polymer on the outside, but this sort of stiffer metamaterial, sort of like a wire, right? In between, the functional form of this really controls the material property of this valve. And so if you think about it, right, this is actually quite an interesting problem where your inputs are functional in nature, right? And then, this comes to the problem of, well, how do we build a predictive model, a probabilistic predictive model, which takes functions as the inputs, and also, in our case, outputs functions as the outputs as well, right? Because the material properties is in terms of a curve, not single value. And so, given the problem of limited data and the fact that the problem, right, inputs and outputs are quite complex, this is where we need some of the physics to sort of constrain the predictive model. And so in this work right here, which, it's sort of like a different flavor of integrating physics, right? Because we don't have exactly, the mechanistic principles necessarily, right, for the problem. But we can elicit certain properties that might be useful. For example, spectral frequencies that might be important, independence assumptions between the curve and the input, all of that stuff. And so this is more of an applied project, but we integrate a lot of these assumptions, these features into the Gaussian process model. And then we build a predictive model which can, for a given new, right, metamaterial input structure, this wire, a new sort of a metamaterial structure, we can predict what the material properties will look like in terms of a curve. Now, like you said, right, there's a lot of parts to this problem, and getting a predictive model really isn't the final solution, right? We still have to address the problem of trying to customize this for an incoming patient, right? And of course, this is one of the problems, as I was mentioning, where the problem itself is much more complex than the papers that, what we try to do is, break the problem up into simpler sub-problems and then, write a paper on that. But of course, solving the full-scale problem is going to require combining all of these methods together, right, in a scalable and an efficient way. But this is really where we use the predictive models, because we then have to find, sort of like solving an inverse problem, where we have the new metamaterial structure from an incoming patient, right? And this can be through a certain CAT scan of a patient coming in. And we really sort of are against the clock, right? The patient needs to get the surgical procedure, needs to get this sort of 3D printed valve within maybe a day. The surgery is in a day. So we have to then, get this curve and then pull it back to our predictive model and find what metamaterial structure would best mimic, we call this thing tissue mimicking, best mimic this sort of material property. Okay. And so there's a lot of things that one has to integrate, right? First, performing this inverse problem can be quite difficult, right? But additionally, we have to also recognize the fact that a predictive model is not certain either. right? So we have to integrate the uncertainties of our predictive model when we're performing the inverse problem. And so that's one of the things that we sort of dealt with within this sort of Gaussian process. We call this thing a function-on-function Gaussian process model, right? It's how to perform this sort of inverse problem efficiently, such that if I have a new patient coming in, right, we're able to get as good a mimicking performance as possible within that tight time frame. And that, again, really requires integrating the physics, because without it, right, either the model takes too long to train, right, in which case the procedure will be entirely useless, or the model will be very, very inaccurate, right, in which case, you can get, again,
procedure would be just as dangerous and
very dangerous procedure. Yeah.
Cool. Yeah, no, I thought that was a really interesting one, especially because just to like recap, basically the idea is that with aortic stenosis, you're creating an artificial heart valve that's created via a synthetic material, and that synthetic material not only needs to essentially fit the actual like physiology or fit essentially the shape of the patient, but it should also have the synthetic properties of that material should essentially have like the strain and stress characteristics as close to organic material as possible. And then what's interesting is that basically effectively like the form of your synthetic material is a function, and some of the parameterizations of that are function too, and sort of the result at the end is a function, and it's an uncertain function at that. And so putting all those things together, it was yeah. Anyway, sorry. I thought it was very cool, and it did seem it was very nicely pieced together. And I thought this was a very good example of how for someone who has effectively done so much research integrating science like all the way through, what was interesting to me about that one is effectively you still kept certain bits parceled between each other. So it wasn't like you try to say, oh, I'm gonna have this one big cohesive thing and stick it all together. It's like, okay, I'm gonna solve this section the best way that I can, integrating the physics. And now that is that correct, or was it more integrated than I? Okay.
No, this is exactly it, and I think that's a really interesting point, because that's especially in sort of talking with the scientists more and understanding their problem, right? It's exactly what you said. We really try to, pull from the problem interesting statistical questions, which are quite novel, right? But are quite useful, right, in terms of addressing this. So again, this is sort of like this two-way procedure, right? One is we start with the problem and filter out interesting statistical questions, address those, and then integrate all of these models together to build a pipeline that works for the practitioner. Yeah.
Cool. If you don't mind me asking, because basically, we've talked about a lot of like this like PDE work and stuff like that. I was wondering just broadly, as a less mathematical individual, as mathematical as I need to be, but not an ounce more. Is the scientific mathematics that gets embedded in some of these models, is it always going to be of that sort of ODE, PDE nature, like the Navier-Stokes equations and things like that? Or, you mentioned monotonicity. Is like sky's the limit with which actual mathematics you can put into these things, or can it spread out? Are there other places where it seems very promising, even if it isn't well developed?
Yeah, that's a great question. So I mean, the examples that I was mentioning previously, a lot of times deal with the actual PDEs or properties of that PDEs that we integrate, right? So and it really, I think one of the considerations that we have to make here is really this trade-off between how much physics we can integrate, right, and what is the computational efficiency of the model that we get. I guess it's really sort of this the spectrum there, right? On one hand, if we integrate all of the physics in terms of the PDE and the full-scale equations from the physics, then it's very expensive to solve, right? And that's where we really need the predictive model. But on the other hand, if we treat everything as a black box, right, then it can be very computationally efficient, but the results you get might not be interpretable, might not be what the scientists want. And so the amount of information that you really want to integrate really has to consider, right, what information you have and how easily this information can be integrated into the model, right, to get an efficient predictive model. And this could be in the form of PDEs if that PDE can be integrated into the statistical model. This can be forms of the PDEs, or it can be physical knowledge, right? Again, going back to that example where if I drop a ball, it's going to go down, right? It's not going to jump back up in the middle of the air. So oftentimes, we can elicit some of these physical principles, right, into our predictive model. And sometimes it's really, and this is some of the work that we explored recently in terms of these sort of manifold embedded Gaussian processes, right? This GPS paper, Gaussian process subspace prediction paper, where a lot of times, right, the physics has to be learned from the data, right? But we know that the physics is embedded in a certain way, right? In fact, in terms of manifold structure. And so the problem building a predictive model is to first learn this manifold and then build a predictive model which can predict the different physics that goes on, right? So again, I think it's exactly what you said. The sky's the limit because scientific information, it's so vast and so many different varieties that for different problems, one can probably elicit, right, a wide range of these principles, right, and integrate them, right, and pull multiple interesting statistical questions for modeling these type of scientific information, right? Yeah, and I would also say that in this case, this probably, this idea of integrating domain knowledge in this sort of integrated way probably extends beyond science, this sort of science integrated prediction problems as well, right? Because, and this is some of the work that we're doing, for example, in finance or even in sort of music composition, right? This is just this recent interesting work where we're trying to embed a lot of these, musical principles into creating composition, right? As opposed to just treating, the data as just data and dumping it within some very complex neural network, some very complex deep learning model, and have it spit out, results, right? So I think this idea really sort of comes into play whenever you're trying to apply predictive models in a wide range of contexts. Yeah.
Yeah, I'm really looking forward to the follow-up conversation on the sort of the latent Gaussian process work and the manifold GPs. I'm definitely looking forward to, just for the audience to know, this conversation is going to be followed up by a subsequent one on the manifold Gaussian process work. And so, yeah, I very excited about that, and just the range of, just essentially integrating that learning process, that learning with the physics, we're essentially saying where it's beyond our ken to know, it must be learned empirically. And then essentially that's going to be tied in directly with the model that's going to be then taking that empirically learned knowledge and providing the next, I guess, predictive step or whatever. I think that is very cool. And, it definitely, it seems to me that it relates back to, it's just one more step along, for example, compared to the heart valve data, where effectively the properties of the tissue are also, they're experimentally discovered as well. So effectively, as opposed to the experiment being before, it seems like essentially your statistical models helping figure out what that experiment should be, and going from there. But for people who think this is really cool, like myself, like, is there some type of like Simon Mack training regime or something you did to get up to speed? Like, you wake up, you do like 100 push-ups, then you eat like a physics textbook and start your day. How do you sort of pick up the domain knowledge that you need to?
Yeah, that's a great question. So my
And
background
quickly, how do you do it quickly? Yeah, sorry.
How do you do it quickly? Yeah,
Yeah.
crash course on this, right? So I didn't have much of a physics background either. But it's really, in conversations, at least for myself, in conversation with physicists. And I think, a lot of the work that I do, right? And that's where really presentations come into play. Because I only have a short sort of amount of time to sort of explain, right, to statistician what the problem is and what type of science there are that would be interesting to integrate there, right? So what type of crash course?
Is it
That's
just
a-
like read and you just figure out Because I know it recently I've been going through so the Oxford University Press has these books called A Very Brief Introduction, and they're effectively like pocket-sized books done usually by like Nobel laureates and other very high up people in the field. And it's usually about 150 pages of an introduction to something. And so I've just been using those and reading them on my run. So basically I pop them in audiobook, and that's what I do. My most recent one I've been listening to Richard Dawkins. For a related one, it's not one of those series, but effectively just like trying to get back to understanding the biological and physical properties of the phenomena that I study, because I'm in patient vital sign monitoring. That is a very phenomenological aspect. Like at my level, there's not going to be the physics that's involved, but there are scientific principles at work that I want to know as well as possible. But yeah, I was just a little bit curious. Like, is it that you you sit down and you say, okay, here's an undergrad paper describing this, here's a tutorial, and you just work through the math and go from there?
No, that's a good question, because it got me thinking a little bit. So at least for myself, right? Again, I didn't have much of a background in physics, and to be quite honest with you, as a statistician, right? You're never gonna have enough background in terms of like actually, for example, you're put on a project in nuclear physics, right? You have to learn on the spot. It's not something that you can pick up beforehand, right? But that's where sort of keeping an open mind in terms of having discussions with scientists, right, and really understanding what the problem is, right, and asking sort of inquisitive questions in terms of these projects. This idea of sort of prior elicitation really comes into play, right? Because we really want to elicit what type of information the scientist has, right? And really understand what the crux of the problem is scientifically, right? It's not trying to think about, look, I have this tool, right? I have this model, and I'm going to try and fit this in every single application that I work on, right? It's really coming from the problem in. It's a problem-solving approach, right? Where you understand the problem, you talk with the scientists, and from there, right, you can sort of do like a guided sort of exploration of what this is, and exactly what you said. Some of these interesting sort of audiobooks, or even just presentations, going to different conferences for these scientific domains, right, may help. But I think that the first, the most important thing is really sort of keeping an open mind and keeping this sort of approach for problem solving, right, rather than trying to fit a tool into many different domains, right? Because in every single problem, the science will be different, and that's where sort of taking this problem-solving approach and understanding what the problem is, and then catering a statistical method for that problem, right, will be very, very helpful.
What do you think on that topic of like different approaches? Do you think that are there other people who basically do something? I wouldn't say orthogonal, because I use the word orthogonal way too often.
I say complementary.
Complementary. Whose their approaches are very different. That you think like, that's a very useful complement. What would be sort of those complementary approaches to what you do? Is it just, for example, the purely phenomenological modeling, where it's just pump this in, assume it's all black box, do our best, and tell us what's coming out? Or is there something a bit more principled in between?
Right.
So even more principled than what you do, and essentially it's going.
Yeah. But I think in this case, again, this is a sort of a trade-off, right? And statisticians and scientists are oftentimes on different spectrums of that trade-off, and different ends of that spectrum. As statisticians, oftentimes we think about the data as just being collected, right? And then we feed it into a model, right? It's more purely data-driven approach, whereas the scientists like to think about things in terms of a purely science-driven approach, in terms of scientific models, building things up from the ground up, right? And so, on that topic, right, I'd say the existing methods for predictive, we call this, scientific, predictive scientific modeling, or predictive scientific computing, right? The standard literature on this and the standard approaches on this are largely deal with just data-driven approaches, right? Taking the data from the scientific experiments and just plugging it into existing models, right, which don't integrate the science. Now, of course, in a lot of these applications, people are finding out that, look, as technology improves, right, as experimental technology improves, as computing improves, right, you know, the amount of data really becomes a problem. And that's where we really have to sort of search somewhere in the middle of that spectrum. And there's been, scattered but interesting work on integrating science within predictive models, of course. Applied mathematicians, engineers have been exploring these directions with different types of models. Right? So people in the applied math community have been exploring this in terms of polynomial chaos, a variety of different models which integrate different forms of scientific information. Now, I think one of the things that sort of distinguish the work that we do from this line of work is we try to integrate this from a Bayesian perspective, right? We think about information, prior information, scientific information, as prior information to feed into a probabilistic model. So really sort of thinking about sort of this modeling as sort of like a prior elicitation procedure, where we try to elicit all the available science from the scientists, right? And this has several advantages, right? One is that, having a probabilistic model, especially in these predictive models, uncertainty is a key component. For example, if you take that heart valve example, if we're not able to spit out the uncertainty of that particular predictive model, this can mean the difference between life or death, right, for the patient. And so it's not just getting the prediction, but also nailing down the predictive uncertainty and reducing that as well. And that's where a Bayesian view of this integration of science, I think, really comes into play. So I think that's a really interesting area. And, as we sort of talked about, right, there's many types of science, many types of Bayesian predictive models that one can integrate this in. We use Gaussian processes, but there can be a wider range of models, right? And this really opens up, at least my view, right, a lot of really interesting directions to explore statistically, right? Many different types of sciences, many different types of models. What's the best one to sort of integrate? How would this sort of, speed up the pipeline for scientific discovery, right? There's a lot of interesting work there.
Yeah, when you talk about the elicitation of priors, because I think that, maybe people who are from the more frequentist side of the neighborhood, when they think about priors, essentially they're just thinking about basic like prior distributions over parameters and things like that, and essentially for that regularization. But that's all well and good, and you can have your hyper priors over your Gaussian process hyperparameters and things like that. But effectively, it's the same thing. It's just regularizing priors over an individual parameterization. But what I think it's a bit of a different step change when effectively you're not just talking about saying, oh, I'm using these to regularize, but effectively like when you're talking about like a functional prior and things like that, where effectively you're saying all this extra information is actually just part of the whole function. It's not just to regularize one parameter. Is that an important conceptual hurdle, or am I just splitting hairs because I'm not?
I think that's a really great point. No, that's an important hurdle, because exactly what you said, right? I'll use the example of Gaussian process modeling. This is something I probably should have explained a little bit earlier, which is, look, a Gaussian process from a Bayesian perspective is really placing a prior model on what the response surface would look like before I observe data, right? And that I would condition on the data that I observe, right? And learn what the function actually looks like. Now, in our case, right, what we try to do is...
just to very quickly interject, just so that people have an idea about it. It's like, so effectively, people who are used to the Gaussian process, they're used to essentially that sausage link description of it. But, that's, and then they usually do something like, okay, we'll just assume that it's a mean zero Gaussian process. And that's already putting in some hard information in there. But, there's nothing stopping me from saying that, like, my prior is a Gaussian process with a linear mean function, or an exponentially decreasing mean function and things like that. So like there's other bits in here that can deviate from that, that's essentially already putting in hard information. Sorry, I hope that
that's a great clarification. So people, at least in the existing sort of a Gaussian process modeling, right, there are ways of integrating information in there, right? Like you said, using different correlation functions, the Matern, Gaussian correlation, using different mean functions if we have that information in. And I guess what we're doing here is sort of taking that one step further and thinking about, look, if we know, for example, if the response surface is monotone, right, how do we build a Gaussian process, right? Or, some form of predictive model, a Bayesian predictive model, which can integrate where sample draws from this process will be monotone with high probability or with probability 1. Or for example, in this case, maybe we have some information about the underlying black box function being generated from a PDE. And we have certain boundary conditions, initial conditions, and all of that fun stuff. How do we integrate that into the probabilistic model such that sample draws from this probabilistic model will give me these properties, again, with high probability or with probability 1, right? Because if we're able to do that, then we have, a way of integrating prior information, right, from the scientist into the model. And all we have to then do is condition on the data, right? And this has several advantages, right? This can improve prediction, but this can also drastically reduce predictive uncertainty, right? And both of these are crucial in cases where, again, I'll pull up that example. You have 5 to 10 data points in 20 dimensions, and you're really sort of stuck if we don't integrate this type of information in there.
Yeah, you can imagine, for example, that sort of like classic thing where the Gaussian process in the posterior prediction starts drooping. It goes back towards the mean when you've basically just said something like, I'm going to, usually they say they, I don't know, make it a mean
Reverse
zero.
back to the mean.
Yeah, it reverts back to the mean. Which, like, I think there's some bits where people say, well, like, are you even Bayesian at that point? If you're already essentially, if you're making it a mean zero, then effectively you're already using the data. You're looking ahead at your data before you're specifying the mean. I deal with enough data where like that's not really the biggest problem that I have to deal with. In fact, I could literally just take some data, use that to calculate the mean, throw it out, and use all the rest. But just an example about how it like reduces the posterior uncertainty. People could imagine you take that usual thing where essentially imagine there's like some curve, and then the Gaussian process posterior droops back down to the mean afterwards. Whereas if you know that it's monotonic, you've now just cut out literally half of all the space, and so you know where it's going to go from there.
And for example, if you know, certain boundary conditions, for example, if you're trying to predict over the space, but right, at this particular boundary on this hyperplane, it's going to equal this particular value, right? That can squish down the Gaussian process right away, right, and give you a lot more information about the problem. And in some sense, that's trying to make the most out of, make the most use out of the data that you collect, which is very expensive, right? And so integrating this information, really has, statistically has 2 advantages, right? Improve prediction, reduce uncertainty, but also from a scientific perspective, and I think this is often overlooked, this also gives a model which the scientists can take a look at and not frown, right? And not be like, have to jump sort of over different hurdles to sort of justify that model, right? Having a ball sort of jump up in the middle of the air. I think that's also quite important in establishing sort of a trust between scientists and statisticians as well.
Well, that is really cool. And Simon, I really appreciate your time today. I'm looking forward to the follow-up conversation on manifolds. I'm hoping that this becomes like essentially a series of conversations. It's going to be a little bit Gaussian process heavy, but I think people will survive.
Well, we deal with other predictive models as well. So,
but yeah, it's not like Harry Potter. You just keep them under the stairs. But yeah, I guess one final question that I just ask everyone at the end, what is, and you can choose whether or not you want to be statisticians or scientists. What is one topic or question that you'd like to see statisticians or scientists debate?
That's a really good question, and I think that's something that I think a little bit about as well. I guess the question of debating is more, I'd say, more discussing, like a topic where they would discuss about how to. I think one topic that would be interesting, and this relates to the conversation that we have here, is for different problems, scientists come again. Going back to that spectrum, right? Scientists think about things in terms of their models, right? And so this is a purely science-driven approach, where statisticians think about things in terms of just data, purely data-driven approach with little science. And I would like to see a conversation, right? Perhaps not a debate, but a conversation, discussion about, where is that optimal point in the in between science-based and data-based learning, right? Which will give you the most bang for your buck, right? Give you the most efficiency for and the maximum power for the data that you observe, which in many cases is very expensive. And this conversation, I think, really is domain specific. And it relates, it can sort of spur a lot of interesting developments in both the statistical modeling literature as well as, how we perform the sort of scientific discovery pipeline, right? Because it involves thinking about, well, what information should I integrate, right? And maybe it's not all of the information, because if I integrate all of the information, I'm basically back at the beginning with the scientific model being too expensive, right? But think about what information we can integrate, what information is important, right? And how do we sort of integrate that model in and give you scientific conclusions which are interpretable, right? Are efficient and, are useful, right? So, I think that's one area where it really deserves further discussions between scientists and statisticians. And I think, I think both sides have to be sort of open-minded and sort of thinking about how we integrate aspects from the other side in terms of building, workflows that are, that can be used in light of these, very expensive, very sophisticated, but very expensive experimental procedures.
Yeah, on that note, it reminded me of two things. One, I'm not sure if you've heard of this, but there's the fallacy of the beard or the fallacy of the pile, where, it's basically just like you have a pile of sand and you take so many things away. And there's no one point where it goes from being a pile to not a pile. Or there's no point in your unshavenness where you've gone from having a beard to not having a beard. And
Fair enough.
yeah, it's an important fallacy where it's basically saying, like, just because there's no individual point which distinguishes, no discrete point, it doesn't mean that there's no difference. Evolutionarily, there's no individual point where our 35 millionth ancestor was definitely a fish versus an advanced primate. But they are distinct species. The speciation occurs despite the fact that there's no single cutoff where this happens. And for me, this seems like one of those problems where effectively my critical thinking is needed, because basically there's never going to be any individual point where definitively. I don't know if it was, maybe it would be an empirical thing where effectively at some point predictions fall off a cliff, you don't like it. Anyway, so that was one of the thoughts that I had. But the other
that really deserves further discussions with, that's where the two communities have to really come together. Mm-hmm. Because I think right now one of the things that's really hindering progress is, it's just this lack of discussion about what tools the other side has and what type of information the other side has as well, right? We're trying to integrate this all together to actually address the problem, right? The problem-solving perspective.
Yeah. The other thing that I was thinking about was, whether or not basically how well respected or how much respect a statistical model will get from scientists. To me, that also seems, as you mentioned, something that's very domain specific, because effectively, when you're talking to a physicist who's extremely comfortable with quantitative models, essentially the reverence with which they have for your model is nowhere near the level essentially someone who's less quantitatively trained. And there are plenty of less quantitative people doing very rigorous science, like lab sciences, for example, where typically, with a few exceptions that people really dig into it, they have a certain number of statistical techniques that they've been trained at, but they're super eager and always happy to have a statistician come in and be like, let me handle this bit for you, because they know it's more accurate. And so I guess the level of scrutiny that would be applied to a statistical model from someone coming very focused in, for example, lab sciences, biological sciences, where they're already doing their own physical experiments, versus the physics area where they've done a ton of quantitative modeling on their own right. Yes. Two different conversations right there.
Exactly. And that's where I think for each of these problems, right, there really needs to be a discussion, right? A careful discussion between the scientist and the modeler.
Cool. Well, Simon, thanks so much for your time. And also thanks for always, just putting forth good, intriguing work. I always enjoy it. And I definitely, Simon's page will be in the description so you can see it and see what I'm talking about. Very cool presentations and very cool work.
Thank you very much, Glenn. This is a great
thanks,
chat.